Hi. Thanks for staying till the end. Today, I just want to talk about some work we've been doing interpreting new glyoxal observations that we've been making from OMI. And I just want to thank my advisors, Kelly Chance and Daniel Jacob, and all the rest of the people at the CFA. So just a bit of background. Glyoxal is a compound that's produced from the oxidation of a range of VOCs. The most prominent of which is isoprene, which is estimated to account for about 50% of the budget, and also a significant contribution from acetylene. It has a very short lifetime of the order of an hour against photolysis and oxidation by OH, and it can also potentially be taken up by aerosol. But what we're really interested in using is the satellite retrievals for is to try and constrain the emissions of some of these compounds as well as perhaps some of the chemical pathways that they oxidize through. Just to provide some context of how difficult it is to retrieve glyoxal from OMI, what I'm showing is some typical absorption strengths that we would typically see for other species in the same fit region. If OMI is like sailing over the ocean, sometimes if the water is really clear, we can see optical depths of the order of 10 to the minus 2. For liquid water, if we zoom in a factor of 10, then you can start to see NO2 and ozone absorptions. And then if you go right to the detection limit of the instrument, glyoxal is kicking around down here. So the key point is that glyoxal absorption is at least an order of magnitude lower than some of these other species. And it makes it very susceptible to interferences. So we've made a lot of updates to our glyoxal retrieval, but I don't really want to dwell on them here. If you're interested, there's more details can be found in a paper that we just published in AMT. So just to highlight some of the differences between our product and previous retrievals, I'm showing results for OMI for winter and summer, as well as the Belgian GOM2 retrieval. And you can see that although the spatial distributions are very similar, the magnitude of the glyoxal columns for the GOM2 retrieval are much higher. So the question is, are these lower columns in our retrieval justified? We can dig through the literature a little bit. There's been one previous inversion done of satellite glyoxal data from the Skiamaki instrument, which it's pretty similar to GOM2. And they had to double their a priori source in order to match observations. But if we look at the surface, our models seem to do reasonably okay. So we believe that the new retrieval might resolve some of this discrepancy. Just trying to guess why why there's some bias in the old retrievals. What I'm plotting here is MODIS water vapor columns for July 2006. And as you would expect, there's high water vapor columns over the tropics and over the Asian monsoon region. And you can see these same features that pop out in the older glyoxal retrievals. So that potentially is a water vapor interference. But it's something that we have to look into a bit further. So there weren't really many concurrent glyoxal observations for the good period of OMI. So we tried to think of other ways we could indirectly validate the retrieval. So we thought about correlations with other species. So if you think about the US over summer, the dominant source of variability in both glyoxal and formaldehyde comes from isoprene oxidation. So isoprene oxidizes, it forms a peroxy radical. In high NOx conditions, it'll react with NO to then form glyoxal and formaldehyde in some yields. And if there's not enough NOx presence, then these other pathways become more dominant. So we can kind of think of formaldehyde as a tracer for isoprene going to products. And if we look at the slope between glyoxal and formaldehyde, it should provide some indication of what the relative yields are. We can also calculate the fraction of the peroxy radical going down these different pathways, which is what I'm showing at the bottom with our chemical transport model. And you can see that over the US in summer, this is in 2006, with a very coarse model run, most of the isoprene is going through the high NOx pathway, about 50 to 80%, with also a significant contribution from HO2. So this should really be reflective of more of the high NOx case when we look at comparisons. So what I'm showing here, the correlations between the two species, on the left is for OMI and the right geoschem. They're in ballpark agreement, but we also have surface data that we can validate our model against. So this is data from Frank Koich's group in Alabama, and you can see that the slopes in the model and the observations actually do surprisingly well. So we think that our models are at least doing okay at replicating the high NOx isoprene oxidation pathways. Another thing we looked at was if you zoom in over the southeast US, the distribution of formaldehyde is actually, the distribution of glyoxal is actually much more heterogeneous than what you would expect from the concurrent formaldehyde observations. And at first we thought this was just having a crappy satellite retrieval. But then if you look at different years, we get similar patterns. We also have aircraft data for glyoxal and formaldehyde measured during SENEX last year. And you can see the same features that may be present in the satellite data. Say if you look over the Ozarks, there's high formaldehyde, but very low glyoxal. And our models really can't replicate this sort of pattern. So there are also aerosol mass spectrometry measurements taken during SENEX. And so we can calculate an aerosol neutralization fraction. And it's one thing that we found that the slope of this correlation between glyoxal and formaldehyde becomes more shallow in the presence of acidic aerosol. So we can either interpret this as glyoxal's lifetime is becoming shorter, or the yield from its sources is becoming lower. But we don't think it's that it's being taken up to the aerosol, or that this can cause that significant of an effect because it already has a short lifetime. Another thing we can look at is the products before it's oxidate that produce glyoxal from isoprene oxidation. It turns out over this region, about 50% is coming from both pathways. One of the key species for glyoxal production is from epoxides, but as we've seen this week, there's been a lot of mechanisms proposed for epoxides forming SOA through like ring opening reactions like this that heavily depend on acid concentrations. So it could be that this acid catalyzed reactive uptake pathway is competing with glyoxal production. The question is this actually feasible? Well, Paul Wemberg's group has been doing a lot of kinetic studies. And what they found was that if you put some of their measurements into just some back-of-the-envelope calculations, that if the aerosol is acidic enough, it can be the dominant pathway of loss for these species. But the problem at the moment is that in our models, we don't have a good handle on the yields of glyoxal from them. So in order to really exploit if the satellite observations are tracing this effect, we would need to know that better. Another thing we noticed when we were gridding our data was that there was always this like really strong hotspot in southern China, which turned out to be over the Pearl River Delta. And in our model, we do a really terrible job at trying to replicate it. So we dug a bit further, and it turns out that the Pearl River Delta is known as China's factory. So there's been a lot of local interest in studying its air quality. And in 2009, there was this inventory published. It was a very high resolution, used very local emission factors and so forth. So it's probably the best guess at the emissions. And what they estimate is that alkanes, alkenes, and aromatic species are the dominant contributors. And also vehicles and solvent evaporation are the dominant sources. So we can use this inventory to try and estimate what that hotspot actually is and what is actually contributing to the glyoxal production. So what we did was that we ran through the entire list of species in the inventory and just calculated their yields using the master chemical mechanism. And the key point to take away is that aromatics are actually the dominant contributors to glyoxal in this region. And formaldehyde is far less selective for the actual VOC species. So we're really tracing aromatic oxidation. We can go one step further and bin the data by wind direction. So what I'm showing here is the PRD plume when the winds are calm, when the winds are blowing from the east, and when the winds are blowing from the northeast. And it might be a little bit hard to see, so I've also ghosted the peak of this calm region, and you can clearly see that the plume moves as you would expect from the wind direction. So another question we can ask is, are the sources in the PRD emissions inventory consistent with this plume movement? So what we can do is we can sort of run some trajectories through the plume, and we can integrate across these trajectories at different points in time. And then we can come up with a line density versus time plot like this one. So we tried fitting, just because our model isn't very high resolution, we tried fitting some just silly 1D reaction advection plume models. So this is using that same inventory, just assuming that some emission at a point source for some VOC, it gets oxidized to produce glyoxal with some yield, and which further oxidizes and gets lost. And what we found is that if we just use fixed emissions, we don't do a very good job at replicating it. But if we then apply diurnal scaling factors to the source categories, we don't do such a terrible job. So I guess the takeaway really is just that where our retrieval is consistent with like a well-studied region from the bottom up. So we believe that it's probably getting to the point where it could be useful in proper inversion studies. So it might be interesting in the future because the total Chinese VOC source is pretty uncertain, and we can maybe combine it with other retrievals like formaldehyde to really get a good handle on constraints to these things. Yeah, and with that, I'll take questions. Thanks.
So we'll have time for a few questions.
Very nice talk. I was wondering, is the NOx in your line model varying, or is it?
Yeah, so I tried fitting NOx plumes as well, like in the belly paper, and I'm just using a mean OH concentration at the moment, but it's diagonally scaled. But I just matched it to a paper that I found. But it seems consistent with the same plume decay. And the wind speeds are fairly constant in the region, so you don't have those same OH effects because it's usually like, because it's like in southern China and the tropics, it's usually a fairly uniform flow and speed, if that